Okay, so good afternoon, everyone. Today we'll begin the introduction to a nanoscience and technology lecture. So we'll wrap up the last lecture where we talked about the effect in nanoscale, especially in the case for the liquid and also for the heat. And then we'll go into the very basics of the quantum mechanics. Okay. So yeah, I mean, in the last lecture, I briefly mentioned about the heat, right? The heat is the source of the energy in our daily life, and all those energy input coming into the earth is actually from the sun, right? So if you remember, right, the heat, right, from the sun, right, gets delivered by in form of radiation. Okay? In Korean, 복사라고도 하고요. 그죠? So last lecture, I mentioned about this importance of heat and the importance of engineering to govern 혹은 이 열을 어떻게 활용하거나 조절하는지에 대한 학문, 공학, which is called the thermal engineering. And it is the very basic field in many engineering or many science and categories, right? So especially in mechanical engineering or in chemical engineering and the material science, thermal engineering is a very classic, important field. So yeah, I mean, I mentioned about this electric cooling, right? All this is happening, and actually, this type of heating problem is the major issue in many electronics, right? So the meaning that it gets hot is there's waste energy. Okay. So I also mentioned that people also want to use this heat energy, right? This radiated energy, right, to convert it into the energy, right? So this is also the important thing. Okay, so I also briefly mentioned about this heat transfer, right? The heat, 혹은 열, right? They always travel from hot to cold, right? And this field of study that determines how much heat or how much energy is transferred or how fast, right? How fast, how fast, how much, or to where. Studying all these fields is called heat transfer. And actually, if you're an undergraduate student, some of you have taken this heat transfer course taught by the professor 최경호 교수님, right? I also teach this course once in a while, right? So this is also a very important field. Okay. So what is heat transfer, right? Again, the heat transfer is a discipline of thermal engineering that concerns generation, use, conversion, and exchange of thermal energy. So basically, like if there is a temperature change or temperature rise, cooling, right, exchange of heat, right, all these is governed by the field of heat transfer. Okay. And this is governed into three main conduction mechanisms, right? So think about it, right? Because 전달 메커니즘에, right? There are several 전달 mechanism. 그죠? 예를 들어서 여러분들이 뭐 예를 들어서 뭐 승훈 학생이 그죠? 준영 학생한테 5만 원을 줘야 돼. 그죠? 그죠? 그러면 승훈 학생이 야 준영아 학식 앞으로 나와. 그죠? 그래서 5만 원짜리를 건네줄 수도 있고, 그죠? 아니면 준영아 계좌번호 불러. 이러고 계좌번호로 써줄 수도 있고요. 그죠? 아니면 야 준영아 내가 캠퍼스 곳곳에 100원짜리 500개 숨겨놨으니까 찾아가. 이렇게 해서 준영 학생이 열심히 찾아다닐 수도 있겠죠. 그죠? Right? 우리가 돈을 전달하거나, 그죠? 뭐 말을 전달할 때도 이렇게 온라인으로 전달할 수도 있고, 전화로 전달할 수도 있고, 그죠? 얼굴을 보고 전달할 수도 있고, 뒤에다 속삭일 수도 있고, 다양한 방법이 있잖아요. 그죠? 그런 것처럼 어떠한 에너지가 다른 곳으로 전달이 될 때, when a form of energy is transferred from one body to other body, or from one system to the other system, there are many ways of this transport, many transport channels. Right? So, uh, in heat transfer, right? There are many mechanisms. So the first thing is conduction. Second one is called convection. And third one is called radiation. Does anyone know what conduction is in Korean? 네, 전도, 그죠? 네, 네, 전도. 오케이. 네. 자, 교회에서 전도하죠. 그죠? 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 그거랑 같은 의미를 가지고 있습니다. 그죠? Right? It's called 전도. Convection is 대류. Radiation is 복사. Okay. If I have to explain all these three mechanisms, I probably have to spend several weeks. Right? But if I summarize that many lectures into 5-minute talk, conduction is the heat transfer basically by contact. Okay? When you touch something cold or when you touch something hot, right? You feel, 그죠? If you touch something hot, you'll be like, oh, ouch. 혹은 아 뜨거. 그죠? When you touch something very cold, you'll be like, oh, 차가워. Oh, it's very cold, right? You can sense that. And that sensation is caused by conduction heat transfer. When you touch something cold, when you touch a glass of soju, right? Let's say this is your hand, okay? You feel it's cold. That is because a certain amount of heat energy is being transferred from your hand to the glass. So there is loss of heat in your arm. So you are losing energy. And when this happens, you feel cold. When you touch hot, it is vice versa. Okay? Okay. The second one is convection. Okay? Convection is happen basically by fluids. 유체입니다, 유체. 즉 고체가 아닌 유체. Right? It's fluid, so it has a fluidic motion. Fluids can be liquid, but it can also be gas. Right? Okay? Everyone knows, right? When you are standing, when there is no wind, you don't feel that cool, right? But when the wind blows, right? You can feel this wind, but at the same time, you feel cool. 그죠? 시원함을 느끼죠. 그죠? Right? That is because this wind comes to you and takes away certain amount of energy from your body surface. So because you are losing energy at this body surface, or because you are transferring your body energy into this fluid, you are losing energy. Okay? So that is basically what is happening here. And that kind of a situation is called convection. Okay? So here is very fun example. Right? If you think about, a bucket of water, right? Okay, and let's say you drop, um, let's say, um, um, hot metal ball, right? Let's say this is copper ball. Okay, if this liquid is perfectly still, okay, 이 물이 아무런 움직임도 없어요. 그냥 가만히 있는 물이야, right? There is this no kind of a flow generation of temperature difference. 뭐 온도 차에 의해서 유동이 생기거나 그런 것도 없이 그냥 진짜 가만히 있는 fluid, right? Then, even though this is fluid, you can call this as a conduction. Okay? However, if there's a river, this is moving fluid, and if you drop a copper ball, right, this copper ball will lose heat, or the temperature will drop majorly due to convection. Okay? Okay. So like understanding how to calculate this conduction, how fast does this copper ball get cooled, right? Or how to calculate this convection. What happens if this fluid speed goes up? 그쵸? 유량의 흐름이 빨라지느냐, 느려지느냐 이런 거에 따라서 열을 손실하는 양이 얼마나 증가하느냐 이러한 것들을 배우는 학문이 it's called the heat transfer. Okay? And also for the last, we have the term called radiation. 복사열, 그죠? This is basically the energy transfer based on the light energy. Okay? So if you think about light, every light is electromagnetic wave. And this wave can propagate in the vacuum medium. Okay? So that is why this light energy can be transferred from sun to Earth, right? And then there is also some term called vaporization. I mean, this you can probably, I mean, yeah, this is also part of convection, but yeah, these three are the major heat transfer mechanisms. Okay. Okay. So again, heat engine, or if you want to transfer heat from cold to hot area, right? If you want to make something more hotter, like hotter, right? Then you need to put energy. So that requires the work. Okay. And also the example, I mean, there are all these examples. So it is a very wide area of study, and actually it is very fun. And if you really like to solve differential equations or partial differential equations, it is the field that uses a lot of differential equations. So let's see, like why people study heat transfer. The human body is constantly radiating heat to its surroundings, and human comfort is closely tied to the rate of this radiation. Okay. Okay. And we try to control this heat transfer by putting more clothes. In winter, it's very cold. So we don't want to lose heat from our body, right? If we lose too much heat, then people die, right? We need to maintain a certain body temperature, right? That's why we put a lot of clothes. Okay, electric or gas range, TV, mobile phones, right? And also heat transfer plays a major role in design of many other devices, right? Solar collectors, power plants, spacecraft, right? Okay. If we can solve the heat transfer problem, we can calculate the optimal insulation thickness. Okay. Okay. So we can decide the certain thickness of wall is sufficient to block the heat loss. Right? So we can calculate, so we can minimize the use of the material, but at the same time maximize the insulation. 그죠? 인슐레이션 하면 뭐 단열, 그죠? 단열이죠, 그죠? So it also plays a big role in economic consideration of designing a building or designing a system. Okay. So again, why heat transfer? I mean, there's a lot of localized nano microscale heat generation, especially in electronics, computer chips, memories, right? And also we see a very interesting heat transfer characteristics in nanomaterials. Again, this kind of a heat transfer is in continuum regime for in a bulk material, but when it goes down to nanomaterials, right, such heat transfer is very directional or exhibits a characteristic that is much different and from bulk scale. And also, I mean, the heat loss is a very big thing. Okay, if we put 100% into a system in a car, let's say, okay, only 12.6% is used to actually move the vehicle down the road. Okay, I mean there's 2% loss in operation, 5.6 loss due to friction in components, also friction between the your wheels and the ground, and also 70% is lost by idling. Idling means that when a car, the engine is running but it's not moving, right? If there's a high traffic, your car stays still but your engine is running, right? And also here, 62% is loss, right? And majority of the 60% is the waste heat. Okay, when you drive a car or when you drive the motorcycle, you should not touch the engine, right? Because engine gets really hot. Okay. Such large heat generation is basically the waste of heat. Okay? Okay. So yeah, I mean, I'm spending about 20 minutes not talking about nano or micro stuff, but I wanted to emphasize that heat transfer interesting field. Yeah. I mean, it can be really hard to some people, but I mean, I know most of you are graduating soon, but if you get a chance, maybe it'll be a good idea to learn a little bit of heat transfer. Okay? All right. So let's begin the fun part. Okay. There is a many materials property. There are many properties related to heat or related to energy. Okay. Um, okay. So maybe I'll ask some questions. 총명 학생, 송총명 학생. 총명 학생, put your hands up. 네. 총명 학생 없나 보네요. 오케이. 그럼 수미 학생. 네. 본인이 제일 좋아하는 물성이 뭐예요? 여러 가지 물성 중에 내가 제일 관심 있고 재밌는 물성. 물성이라고 하면은 물질의 특성이죠. 그죠? 뭐 열전도, 전기전도도 될 수 있겠고요. 뭐 여러 가지가 있어요. 비투가열도 뭐 물성이고요. 여러 가지가 있는데 아니면 혹시 딱 떠오르는 게 없나요? 네. 알겠습니다. 갑자기 불러서 당황했나 보네요. 네. 그러면 선우 학생 반갑네요. 선우 학생. 선우 학생이 제일 좋아하는 물성. 점도 네. 요즘 비스커스한 거를 많이 만지시나 봐요. 그죠? 네. 점도 오케이. So 선우 mentioned viscosity, right? I mean, as I said, there are many properties of the material. Okay? But also there are property. 네, 선우 학생, 수미 학생 감사합니다. 총명 학생 아는 분은 카톡 좀 날려주세요. 어디 갔냐고. 네. 오케이. 네. 자, 그러면 so there are some properties those are related to heat. Okay? And the heat capacity is one of them. Okay? So what is heat capacity? It's called here. Okay. So here is the definition of heat capacity, right? Heat capacity C equals energy divided by change in temperature. Which basically means heat capacity C is amount of energy to induce 1 degree Celsius or 1 Kelvin change in temperature, okay, forget about this. So it's the amount of energy to induce 1 Kelvin or 1 degree Celsius change in temperature of a material. Okay. In other words, it is the amount of energy that material can store for 1 degree Celsius difference. Okay? Good. Okay. So if you look at a lot of these materials, they have all these values. And as you can see, they are all different. And when you talk about this heat capacity is a function of L3, so it's a function of volume. Okay. So if you are big or if you have more fat, you can store a lot of energy in your body, right? Okay. So so if you so yeah, I mean the healthy fat, okay? So I have a lot of fat. 여기서 fat에서 말하는 건 지방이에요. 뭐 절대 인격 비하나 이런 거 아닙니다, right? So I have a lot of fat in my body, right? So I can store a lot of energy, okay? Right? Okay. So that is one case. Even though it's the same material, depending on their volume, the total amount of energy they can store is different. Okay. All right. So that is the case. And also, depending on materials, there are different materials, different heat capacity values. So certain materials, such as hydrogen, right? They can store a lot of energy. Ethanol, paraffin, water, they can store a lot of energy, right? In contrast, all these metals, they don't really store a lot of energy. Okay? Okay. If you think about our body, right, there are muscles, there are fat, and there are bones, right? So there are fat, there are proteins, and there is 탄수화물이 carbonates, maybe, I don't know. But like, yeah, they all have different heat capacities. Okay? Okay, so that is one example. Okay. The heat dissipation, right? Heat dissipation basically means 열손실, 그죠? 뭐 소위 말해서 우리가 말하는 근손실 이런 거 있죠, 그죠? 그렇잖아요, 열손실, right? Every time we are losing heat, if you have the air conditioner on right now, or if you feel a little chilly, 약간 시원하다고 느끼고 있다, then that means that you are losing heat. Your body dissipates heat, right? Your body is radiating heat all the time because your body temperature is generally higher than your environment temperature. However, we cannot see such radiation. 자, 여러분들의 몸은 발광을 하고 있어요. 그러니까 발광하면 그 발광 말고 빛을 발하는, 그죠? Your body is radiating heat. Your body 몸은 발광을 하고 있어요. Right? We cannot see it, right? Because such wave is an infrared region. 여러분들의 몸은 자외선을 발산하고 있기 때문에 눈으로 못 보는 것 뿐이지 여러분들 모두 이렇게 빛을 하고 있어요, right? Right? Like that, everyone is dissipating heat. Okay? Right. So you can dissipate heat in many different mechanisms: conduction, convection, radiation, and also vaporization. Okay. Of course, people cannot vaporize. It's a very horrific situation if you vaporize, 그죠? But anyways, so when you look at this convection, generally our body, right, radiates most heat by radiation, but we really don't feel it, right? But convection, we can feel it. If you turn on your fan, or if you turn on your air conditioner, or if there is wind, or if you jump into the water, right, you feel that heat is leaving you. You feel cold. And this is called convection heat transfer or heat dissipation. And there is a famous rule that governs this convection heat transfer. Is called Newton's law of cooling. And this Newton is that Newton that you are thinking about. 여러분들이 생각하는 그 뉴턴 맞아요. Okay? Newton. Yeah, this is Newton, right? Okay? Okay, Newton right here, right, with the shiny apple. Okay, yeah, I mean, sorry, I'm just fooling around with my tablet. But yeah, so this is the guy, Newton of cooling, right? So let's consider this. Let's consider there is a solid body. Okay, with the surface area A. Right, and the temperature say TW. Okay, and there is a wind blowing. Okay, at the speed at the velocity or speed of u infinity, and also the ambient temperature T infinity. If if the temperature of this wall or substrate is higher than this ambient temperature, right? Then, right, this part is hotter, so it has to dissipate heat. It has to lose energy. And to calculate this amount of heat being transferred, this equals H times surface area times the temperature difference between two, and this H is called heat transfer coefficient. Okay. Yeah, I mean it is not a fixed value. It is a very complex coefficient that can be calculated. It depends on the flow velocity, the Reynolds number, right? It depends on velocity, Reynolds number that we talked before, and like it also, yeah. So Reynolds number, so it is depends on temperature, the viscosity, right? 점도. So it depends on a lot of properties, right? But what I'm trying to say is that in many cases, radiation, conduction, convection, no matter what the mechanism is, the heat or the energy in your body or the energy stored in one system gets dissipated at the surface interface. 어떠한 시스템, 어떠한 동물, 어떠한 인간, 내면에 다 가지고 있는 에너지는 표면, 그러니까 그 에너지를 가지고 있는 물체와 외부 환경과 맞닿아 있는 부분에서만 이 exchange가 일어납니다. 열 교환 혹은 열 전달이 일어나요. Right? And that interface is the surface. Okay? All right? So, yeah. Um, that is the situation here. Okay. Okay. So I wanted to say that all these scales down. Right? Okay. So the reason that I'm giving this thermal thing is that if you look at here, I'm sorry. Okay. Okay. Is that when, as I said, in nano, all right, in nano, right? What I have said is the ratio of surface area to volume is very, very, very high. Okay? Okay. What is area? Area is related to dissipation. Volume is related to stored energy or how easily the temperature gets changed. Okay. So what this really goes to is that in nanoscale, in nanomaterial or nanostructures, they can lose heat very fast or they can receive heat very fast. And also, their temperature can change very rapidly with the minimum amount of energy. Okay. So let's say if you have a water, if you have a hot pot, 냄비가 있어요. 물을 끓여요. 자, 어제 라면 드신 분, 손. Anyone who ate ramen yesterday, put your hands up, please. 네. Cherish, you ate ramen? Okay. 진웅 학생, 기호 학생, okay. Okay. 네, 알겠습니다. Okay. 자, 장한 학생도 먹었어요. Okay. Alright. Hey, Cherish, which ramen did you eat? Shin ramen? Pork dumplings? Okay. Okay. 뭔가 새로운 건가 보네요. Okay. Cool. 장한 학생은 어제 라면 뭐 먹었어요? 닭볶 왕뚜껑. 아, 예. Okay. 컵라면이네요. 아무튼 okay. So let's say 왕뚜껑, right? So 장원 wants to cook the 왕뚜껑, right? He has to boil the water. Okay. If you think about the hot pot, right? The volume of water, which is about 500 milliliter, right? And the place where the heat gets transferred is the bottom surface of this pot. So you have certain area. So if 장원 has very efficient 뭐 레인지 혹은 the radiate the gas stove, right? Maybe it'll take about like 2 minutes to boil the water. However, let's say Sonu, right? Sonu is working in Professor Soko Park's lab, and she's working in the field of micro robotics or software robotics, and she is making this, I don't know, like droplet shaped liquid robot, right? Its volume is, let's say, 50 microliter, right? But here, the entire surface is surface. The surface area to area, volume is very high. That it can take about like 2 nanosecond or 2 microsecond to boil this droplet. Okay. So yeah, maybe I'm spending too much time explaining the very obvious thing, but what I'm trying to say is that even though it is the same material and it keeps the material property stays constant, by changing their dimension, we can, oh, sorry, let me turn off my cacao. I mean, it's my wife again, but, okay. Okay. So it is my wife asking me to which coffee to drink, and yeah, so yeah. Okay, well, yeah, that is life. But yeah, anyways, so what I'm trying to say is that even though the material property is the constant for the same material, by designing their dimension in a right way, we can totally change their behavior. And we just learn the behavior in heating or behavior in changing their properties. Okay? All right. Okay. Well, thank you for volunteering, Taiwan, Cherish, and some other two students. Okay, thank you very much. Okay, so there in heat transfer, I mean there are many dimensionless numbers, just like Reynolds number in fluid mechanics. In thermal energy or heat transfer, there are many numbers. The one of the best number that I like is called the Biot number. Okay, and this Biot number is a dimensionless quantity used in heat transfer calculations. The ratio of the heat transfer resistance inside a body and at the surface of a body. Okay, what this means is that what this means is that as I said, when the material is small and when material is big, okay, even though there is the same temperature difference between this object and the environment, same delta T, right? The time to reach thermal equilibrium or 열평형 is different because of their size. Okay. And also there is this concept of heat transfer resistance, all called thermal resistance. I'm pretty sure many of you are very familiar with the term resistance, right? In an electric circuit, there is a resistor, elect which resistances to the flow of current, right? It gives certain value of resistance in ohms, right? And it hinders or it hinders the hinder하면 뭐 방해하다, 그죠? It hinders the flow of the current. Okay, there is a very similar concept in thermal resistance, right? So yeah, this is thermal resistance. Okay, so basically, the material with the very high thermal resistance is a good insulator, or it can make this temperature change to happen at a very slow rate. Okay? The material with the very high thermal resistance is wood or like glass, amorphous glass, right? These are the example. Okay. So if you think about it, right? Let's say so this is the heat transfer coefficient, and this is the characteristic dimension. So the top is convection, and the bottom is conduction. And the unit of conduction is watt per thermal conductivity. Okay. Okay. Right. When Biot number is much smaller than 1, or when this thermal conductivity is much higher than convection effect, right? This solid has a very high thermal resistance. Okay, so a lot of heat transfer will happen at the interface, and the change inside the ball of the temperature is very small, right? So it means that temperature inside the body is very uniform. When the Biot number is much higher than 1, okay, right? The heat change due to this convection effect is very fast. It's much faster than happening at the conduction effect. So temperature varies at different positions inside a body. So when the Biot number is very big, there is this temperature variation. Okay, maybe let's say if this ball is hot. Okay, let me erase all these. Let's say we have a really hot ball. And let it drop to the cold water. Okay, all right. If this ball has a small Biot number, this hot ball will reach whatever the thermal equilibrium temperature at a very fast speed. And the temperature inside this ball, right, will be uniform. However, if this ball is really big, right, when you drop this ball into the water, the surface of this ball, the temperature will drop, but inside will remain hot for a certain time. So there is this temperature difference within this solid. Okay? And if you look at here, even though the material's thermal conductivity or the heat transfer coefficient, which is determined by the environment, does not change over time, or does not change, is not a function of size, right? So it remains the same. If we make the material very small, right? This is the L, length. So in micro or nano, this L is really small. So in most cases, the Biot number is much, much smaller than 1. Okay? So what this means, for micro nano system, we can simply assume that the temperature inside a body or the temperature inside the object is uniform. Okay? Then what does this mean? Why is this important? I mean, the best part of this is this makes this micro nano sized device or the object, it becomes a very, very simple problem to calculate heat transfer. Okay? So when you design, or in other words, when you deal with this micro nano materials, right, you really don't have to care about this temperature difference effect inside this material. Okay? Okay? So it is a very simple problem to solve. Okay? And then this is a really, really great advantage in the field of heat transfer. Okay? Okay. So when people see this nano or micro devices, they usually can not neglect, but I mean, the temperature effect is very small. Okay. Or the like gravity is small, right? I mean, you don't really have to think about the temperature difference inside your device. Right? Okay. Or if you have to change the temperature of your device, right? If you have to change the temperature of your device, you just need to put very small energy. Right? So there are many great advantages in terms of heat for this material. Okay. All right. So yeah, I mean, I'm spending too much time here, uh, but it is a important concept. Okay. So yeah, yeah, I think I've been talking too much. So maybe I'm sorry. 죄송합니다. So maybe we'll take a break for 5 minutes, and in the meantime, I'll call the attendance. 네. 출석 좀 부를게요. Okay, so and it's a long class, so let's see. So okay, okay, okay. So today's September 10th. Okay, 네, 한번 출석을 쭉 불러보겠습니다. 잠시만요. 이게 온라인 강의 때는 이 순간이 되게 참, 네, 그래요. 아무튼. 이거 뭐, 이거 왜 이러냐, 시스템이? 잠시만요. 출석부에 12명밖에 안 보이는데, 네, 오늘은 그냥 스킵을 할까요? 잠시만요. 아니다. 그냥 지금, so I'm gonna take the attendance. So if you are listening to me right now, can you please raise your hand using the raise hand option below the screen? So if you look at the screen, in the below, there is a microphone, there is a video, and then there is this icon with the human hand. Okay. 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 So what I'm gonna do right now is that 총명 학생 왔어요? Okay. 네, 알겠습니다. 네. Okay, welcome back. So what I'm gonna do is I'm gonna print this screen and save it to my lecture. All right. All right, done. September 10th. All right, so okay. 죄송합니다. Okay, so okay. 손 내려주셔도 됩니다. 감사합니다. Oops, I'm sorry. 죄송합니다. 여러분들 지금 제 얼굴 안 보이시죠? 보여요? 빨리 넘겨야겠다 이거. 갑자기 보여서 좀 짜증나겠어요, 그죠? Anyways, so let's go to scaling color. Okay. So for color, we'll also learn about color, but I remember that one student said he or she wanted to learn about the quantum dots, right? And again, 네, lecture사 PPT인가요? PPT입니다. 제가 따로 업로드 했어요. 제가 안 했나요, 업로드를? 안 했네요. 아이고. 네, 지금 할게요. 업로드를. 잠시만요. Okay, I have just uploaded lecture 4. It's my apologies. My bad. Okay. Well, thank you. 영재 학생, 영재 학생 감사합니다. So there is a scaling color, right? Bulk gold appears yellow in color, and nano-sized gold appears red or even transparent. Okay. So the color, okay? Every material has its own color, right? And we are very familiar with the visible light range from 빨주노초 파란보, right? Red, orange, yellow, right? The rainbow colors, right? We can visualize those colors. And as I said, soft materials has this color. As I said, the color is the appearance of light. The color is happening because the material interacts with light. And as I said, light is a form of electromagnetic wave. Right? And so there is like a phonons, right? Right? We'll also learn about this concept about like phonons. Right? These phonons or electromagnetic wave particles, right, they will interact with this gold. And actually, they are going to interact with their energy band structure. We'll also learn what the energy band is, but basically they do some interaction. This electromagnetic wave, which is light, interact with this material. And at surface, right? Okay. These phonon energy will be transferred and induce movement of electron or something, and then it'll give out certain color depending on their properties, right? Optical or electric properties, right? When the size of the material becomes really small, right? In bulk gold, it's really big, so electron can freely move around without any trouble. But when the material becomes really small, the electron will be bothered. The movement of the electron is not free. Okay? And this limited electron movement induces change in color. So this dimension is the wavelength, is the size of those gold nanoparticles. Okay? And they react differently with light, absorbs visible light or so. Okay. So what I'm saying is here is that by just controlling the particle size, we can change their property, their optical property, and we can change their color when they interact with light. Okay? Okay. And one of the very famous example is the quantum dot. So we will learn more about this quantum dot later in this class. Okay. And maybe if possible, I'll also explain about this QD-TV by Samsung. Right? And LG is OLED. Okay. Okay. So yeah, I mean that light is also example, right? So before we go in, right, about 3 minutes ago, I mentioned about this light, phonon, electron, the energy band structure, right? Electron movement, right? All these things, right, maybe are not familiar to you, right? I mean, if you took the semiconductor physics or the semiconductor materials, then the band gap, energy band structure, Schrodinger's equation, all these are very familiar to you, right? But let me give you a very basic introduction to the nanoscale of physics. Okay, so 1 mole consists of these many molecules. Okay, water, 1 mole is 18 grams. Melting point of 1 mole, melting point of 10 to the 10 moles. Are they the same? The answer is no, and we'll learn why it is no. Okay. The property of materials change in nanoscale. Okay. And they are in no longer continuum regime. They come to the Newtonian physics. So what the continuum regime is that when a system or the system's behavior can be predicted using and using on some how should I say using an equation, or the behavior can be predicted by using an equation or using on a mathematical analysis. Okay. So in continuum, if there is a ball, it has a vector, right? Okay, with a certain direction. Let's say it's 1 minus 1, right? And you know the magnitude, right? Then let's say after, and it has a speed of what, 2 meters per second or whatever. Then after t 10 seconds, you can predict the position of this ball. Okay, that is continuum regime. However, when the system gets really small, then it becomes subcontinuum, or it is called the discrete regime. Okay. Right. And the field of quantum mechanics solve this part. When things become too small, all right, it becomes really hard to solve their behavior using these continuous equations, right? Because the materials behave, right? It's really hard to predict the movement of single electron. I mean, if you have a dozen billions of electrons, right, and if they're moving, right, right, we can predict that billions of electrons. We can take an average and we can predict their behavior, right? But if you account for all these single electrons, it becomes very complex, and it becomes nearly impossible to do so. So in quantum mechanics, we solve everything in terms of probability, which means if we have very small particle in a very small space, we cannot exactly solve where this particle will be after 10 seconds. In quantum mechanics, it's really hard to predict. But what we can do is, let's say if this is the position, one of the position, we can calculate the probability. We can calculate the probability of this ball falls into this area. We can calculate that probability. So we solve everything in terms of probability. So that's the beauty of this quantum mechanics. So, how many of you has taken this quantum mechanics class or have learned about the basic quantum mechanics? 뭐 양자 역학이나 양자 물리 수업 들으신 분 있어요? Anyone? 아, 명지 학생. Okay. Yes. 아, 네. All right. Then for those of you, the next 1 or 2 lectures will be very easy. Okay. I mean, I'm not gonna go into all these equations. I mean, I'm not qualified to give lectures in that part anyways, but I'll do my best to give you the concepts. Okay. Again, the quantum mechanics is the science of the very small. It explains the behavior of matter and its interactions with energy on the scale of atoms and the subatomic particles. So it explains the behavior of matter and its interactions with energy on the scale of atoms and subatomic particles. So when we go to the very small scale, where we have to analyze the movement of these atomic scale, right, then we have to apply quantum mechanics. In a very small system, the particles can behave like wave. Okay. Again, optical energy are being transferred by photons. 광자, right? Electrical energy, many of them are transferred by electrons. 전자. Okay. Acoustic energy or heat or vibration energy, right? acoustic 뭐 음파가 될 수도 있고요. 그죠? 여러분 스피커 앞에 있으면 둥둥둥 베이스 돌릴 때 막 머리 흔들리죠. 그죠? 뭐 클럽 가시거나 나이트는 안 가시나? 네, 아무튼 예. 저도 안 갑니다. 근데 이제 이렇게 둥둥 하면은 이제 느껴지죠. 그죠? Right? That kind of acoustic energy, right? phonons. 그죠? phonon. 그죠? 한국말로 뭐였지? phonon이? Well, anyways, right? So like right, there are all these different waves or particles that behave like wave. Okay? And also for different materials, the dominant energy carriers, as I said, gases, they are molecules. Metals, they're electrons. Insulator, they're phonons. Okay? Okay. So here, if you look at metals, the electrons are the dominant energy carriers. Electrons can carry electrical energy. Okay. So metals are conductors. 도체죠, 도체, right? Insulators, they're phonons, right? So majority of the energy is transferred by in terms of vibration or in form of heat. But phonons cannot carry the electrical energy. So insulators are insulators. I mean, this is budochik, right? That's why insulators cannot transfer electrical energy because phonon is the major carrier. Okay? So every particles, all these, right, behaves like wave. So let's look at light first. We talked about photon, electron, and photon. So let's look at the electron, photon first. 빛광자 이거 맞나요? 네, 뭐 아무튼, right. So if you look at this, the light, right? Light again is the form of electromagnetic wave. Okay. It's a wave, and its color or energy or behavior depends on the wavelength of this light or the frequency of this light. So in general, when this wavelength is, so wavelengths usually use lambda here. So when lambda is low, frequency is high, energy is high. When lambda is high, frequency is low, and energy is low. Of course, the color is different, but the wavelength of this electromagnetic wave basically determines its color or its energy and many other things. So, so if you look at, so this is the total light spectrum, let's say, coming from the sun. And this is the wavelength. This is the visible spectrum right here, which usually ranges around from 300 to 650 nanometers. This is the wavelength of the visible light spectrum. Okay. The majority of the many of sunlight falls into this regime, okay, which is in the visible light spectrum. So because the sunlight, right, that reaches the surface of Earth has this kind of a spectrum, human or many animals have evolved their vision system. Their eyes has been evolved or optimized to this spectrum. 자, 해에서 오는 굉장히 넓은 영역대의 빛 중에, 그죠? 가시광선에 달하는 부분이 굉장히 많이, 상당수가 제일 높은 그 많은 양이 이 영역에 있기 때문에 우리 눈이 이 빛 영역을 잘 볼 수 있게 진화를 한 거예요. Okay? Maybe there are some animals and they have different visible light range, right? I've heard that the bats, right? They can see some infrared, right? Dogs, cats, every animals have slightly different visible range, but generally human, right? We have evolved to see this visible light range. Okay. And then this range right here is all IR, infrared. And if you think about it, the infrared region is really, really big here. Okay? It's really, really big here. So there is also a very big field investigating and also trying to use this light range, right? But yeah, that this is the case. So here, this is the wavelength here in the bottom. There are very wide range of waves. Okay, right? And the actual visible light from is very, very small region. And when it goes to smaller wavelength, from visible to the UV to the X-ray, this light energy is too high. It can be harmful to people. Okay, Gamma rays or X-rays are used for medical purposes. 그죠? 뭐 감마 방사선, right? The nuclear plant meltdown, right? There is a large radiation of nuclear material. Those are the gamma ray region. 그죠? 이런 레이에 피폭이 되면은 뭐 많이 못 살아요. 그죠? 엑스레이도 많이 찍으면 당연히 안 좋고요. 그죠? Right? The UV, right? We put this sun creams to protect our body from this UV light. Okay? And then there is this visible light spectrum. Okay. All right, and then there's infrared, the microwaves, and this radio waves. Radio waves are everywhere, right? If you turn on your radio, it turns on at every position. Okay, right? I mean, yeah, right? Well, NBC, FM, right? KBS, CBS, right? They are all, you can listen to those radios because these radio waves are everywhere, right? But we don't really feel it. We don't get disturbed because their frequency is so low, right? And they are not really interacting with our, and they have very low energy, so we don't really feel them. Okay, all right. So this was the very short introduction to the light. Okay, and then, and starting in the next lecture, I will go into the wave function and some other parts, and then I'll talk more about these nanoscale light and also the electrons or phonon behaviors in the coming lectures. Okay, there. Okay, so